and discovery of ultraviolet radiation. Just read both the passages carefully, and then we'll start with the Maxwell's equation.
Okay.
Okay. So this is how these two radiations, these two electromagnetic waves have been discovered. Alright?
Okay.
Now, let's talk about the Ampere's equation for electromagnetic waves. Okay, yeah. There are four equations, four basic equations. One, two, three, and four. If we talk about the first three equations, these are the three basic equations, and we studied it as well. That with the new term that Maxwell added to Ampere's law, I'll explain you how Maxwell added a new term in the Ampere's law. But before that, let's talk about the three equations of Maxwell. First one is Gauss's law. We have heard this equation before. The electric flux must be equal to charge enclosed divided by epsilon. We have heard that, right? Hello?
Yes.
Yes? In Gauss's law, we have discussed this, that the charge enclosed, the electric flux is always equal to the charge enclosed divided by. We have discussed this. Phi v is equal to 0. Now, what does it mean by that? It means that magnetic flux is 0 or the poles of the magnet can't be separated. Actually, Virat, this set of equations tell us that the magnetic flux is zero when the poles of the magnet, the poles of the magnet can be separated. It means that we can't be able to separate the poles. Means uh, the poles, north or south pole, can't be segregated because if we have a magnet, we have discussed this in the magnetic field chapter that south, and if we break this magnet, the other new magnets have their own north or south pole. So we can't be able to separate out both the poles of the magnet just like the charges. That for suppose you place positive charge over here and negative charge over here. But if we talk about the magnets, we can't be able to separate out its poles just like the charging. So Gauss's law for magnetic fields, absence of magnetic poles, magnetic monopole. We can't be separate out the monopole. Monopole means single pole. The pole will always be situated, always be attached to each other. Okay?
Okay.
Okay. Now the third part, E parallel H. What is this period? E times delta S. If you remember the formula of
Electric field.
voltage, electric potential's formula is E times del S. Okay?
Okay.
So this is E, this is V is equals to E times delta S. So we replace this by V is equals to minus delta phi over delta T. Now what is V?
V is voltage.
V is voltage, or can I write like this? V is EMF
Yes.
also. So isn't it the formula of Faraday law of electromagnetic induction theory?
Yes.
Yes. That's why it's called Faraday's law. Okay.
Okay.
Now let's talk about the last equation in detail, because that's the law in Ampere's law and Maxwell's addition. Let's talk about this. Law in Ampere's law and Maxwell's addition. So let's consider a wire Let's consider a wire having current passing through it. I I current is passing from this wire. Okay.
Okay.
Now, according to Ampere's law, Kira, what would I do to find the magnetic field of the wire? What would I do? Hmm,
To,
What would I do, Kira?
to find the magnetic field of the wire using Ampere's law, you
Yes.
wouldn't you have to
What would I do?
multiply the current enclosed with the 4 pi times 10 to the power negative 7?
No, that's the formula. What would I do to find the magnetic field of this wire? Because we know that current produces magnetic. It means that magnetic field is all over the place. Now tell me, how can I find the magnetic field? You can find the magnetic field by placing Amperian loop over here. Okay.
Okay.
Now we know that magnetic field is evolving around it, around this, okay, in a in an anti-clockwise direction. All right.
Okay.
Now this is a simple task, and we have seen this that by placing or by applying an imperial lobe around the conductor, we can find the magnetic field. So I should write like this. Del L is to find I enclosed. Why do I use integral sign instead of this? Here we know that integral is also a summation. In integral, we summed up the power of the variable, right?
Right.
Sum up. So integration and summation is almost the same thing. Okay. And what does it mean by this circle? Circle means we are finding out the integral of a closed body. So that's why we use circle in the middle of the integral circle. Alright? Okay, now here comes a interesting part. And what is the interesting part? The interesting part is that here we're gonna फिर आप Now I place a capacitor over here. Now this is a capacitor, two plates of capacitor. Now this is the example where Ampere's law gives a faulty result to us. How? Let's see. फिर अब my task is to find the magnetic field between the plates of the capacitor. Between the plates of the capacitor. Okay. In here, Pira, if we talk about this, we need to find the magnetic field at this point P. Now, my task is to find the the magnetic field So I just place an Amperian loop with the same size and at the same point I need to find the magnetic field over here. What do you think, Pira? What will be the magnetic field be? Because the current is constant all over the place. So, is this possible that the magnetic field here is constant as well? Or suppose the magnetic field at point B is written as BP. Now, what will be the value of magnetic field according to the Ampere's law?
If the current is the same, then wouldn't the magnetic field also be the same?
If we talk about the value of current between the plates, the magnetic field between the plates, the current between the plates is zero. Let me just rephrase my words. The current, the wire attaches to one plate of the capacitor and then it attaches to the other plate of the capacitor. In between the plate there is no wire. So, in between the plates there is no current passing through. So, according to Ampere's law, there is no current enclosed. There is
no current enclosed.
No current enclosed. Okay. So I should write like this, that there is no current between the plates of the capacitor. There is only vacuum. So फिर according to the Ampere's law, According to the Ampere's law, the magnetic field is zero, right?
Right.
So it means that BQ is zero. But now here's the interesting part comes up. But according to it, but this is the theoretical part. According to the theory of Ampere's law, there is no there has to be no magnetic field in between the plates of the capacitor. But according to the experiment mirror, according to the experiment, the magnetic field at Q is equal to the magnetic field at P. It means that dq must be equals to bp beta. But how is the Ampere's law is wrong? No, you can't say that. Beta, can't say that. It means that there is something else that generates magnetic field other than the current, other than the current. Alright?
Okay.
Because we know that there is no current flowing in between the plates. Because for suppose the positive charge is placed over here and the negative charge is placed over here. Right?
Right.
So the charge is continuously building up, but no current is in between the plates. So now what Maxwell explains us, Max, Max, Maxwell explains that maybe current is not the only thing that generates magnetic field. This is a very important point, Peter. Maxwell he said maybe the current is not the only thing that generates magnetic field. Okay? So we have to miss something, or you can say that amperes must be missing some part by which we can say that the magnetic field can be produced by any other factors. Okay?
Okay.
Now, what he did, Pira, he because the electric and magnetic fields are moreover same, the sources and the results are moreover the same. So he started explaining like that Now let's recall that how electric field generates. How electric field generates, Sarah?
When it passes through an area,
Sorry.
when it
No. How electric field generates, Sarah? Hmm? How electric field generates. The question is how electric field is generated.
do a charge, moving charges.
Not about moving charges, just a charges. By charges.